All right, so what we're going to start talking about today is just kind of some of the acute effects of altitude. What's going on when we actually are starting to go up in altitude in terms of what's going to be happening with the body. So, again, acute effects of this. Then, after this one, we'll look at what this does to exercise at altitude, and then finally, we'll start talking about some adaptations that happen at altitude. So, altitude is lower pressure, that hypobaria, versus versus the idea of hyperbaric. So that's more than. So one of the things that we know, and this is one of the things you'll see, we talk about millimeters of mercury. Sometimes they also refer to this as torr. An Italian guy by the name of Torricelli was the one that kind of came up with a barometer back in the day. And then over time it was kind of determined that different gases contribute to this pressure, this barometric pressure. And then it was about the 1800s that they started realizing that each of the gases kind of acted separately. And about the time they started doing hot air balloons is when they really started determining some of these effects of hypoxia on the body. So some of the earliest ones with this, they did do some barometric chambers in the mid 1800s, making the chambers large enough where they could build a decompression chamber and determine what was going on with that. Was also this gentleman, Paul Burt, was the first one to determine that decompression sickness, the bends, was actually bubbles in the blood. Like I said, it was in like those mid 1800s when they started doing a lot of these ballooning experiments. Is where they just started determining like the ideas of what was going on with high altitude, and they determined in some of these ones it was pretty crazy. There's actually a movie on, I think it was on Amazon Prime, that was talking about some of this. It was not the right people in it, but some of these ones were the high altitude records. Some of these balloonists were able to reach about 7 miles high, which is higher than Mount Everest. So that's about 35,000 feet, about where a plane is going. And they had these folks in this one lose consciousness, lose the use of their hands, and was finally able to pull the cord with his teeth and get back down. That being said, some of the birds that they had with them were not affected whatsoever. And again, it's another one kind of talking about the little story about some of these ones with the lack of oxygen getting up to different heights. And you can see on this one, they rose up to about 8,600 meters, which is about 8,000 meters is a little bit above Everest, is right around, is a little over 8,000 meters. And they all passed out. They regained consciousness a couple of times, and kind of actually in this one, they ended up going even higher. But luckily they came back down, but 2 of its passengers were dead and only the 1 guy survived it. So again, this is where a lot of this effects of hypoxia started getting figured out, this high altitude and what happens to the body. So one more things we're going to see here is it's really, altitude, we're going to see has a lot to do with physiology that we talked about back in A&P. A lot to do with these partial pressures and the amount of gases that there are in the environment, and along with how much atmospheric pressure there is. We're going to see that really sea level, you don't have, altitude is really not going to affect the body much. And it's even up from, so and these are in meters, so 2,000 meters is about 6,000 feet. So low altitude even up to about 5,000 meters is 5,000 feet is about 1 mile up is where you really do start seeing any effects of altitude on the kind of respiratory physiology. Again, if you were to try to exercise at these ones, you might see some of this, but might see some performance decreases. But again, you can get those back with acclimation up to about that 5,000 feet. When we start going another 1,500 or another 2,500 feet or more, we're going to start seeing, so another 1,000 meters would be another 3,000 feet. So you start getting up to about 8,000 feet. You definitely, if you've ever been up that high in the mountains, you can tell that there definitely has some effects on the body. A lot of times you'll have a headache. definitely a decrease in aerobic capacity, any type of exercise performance. And again, depending on how much higher you go up, you may, at some level, sooner or later, altitude, even if you're acclimated to it, is still going to be a performance hindrance. Again, it has a lot to do with just the fact that there is not as much oxygen available to the body. And sooner or later, that will affect VO2 max, and that will affect aerobic capacity, definitely. Once you get into these really high altitudes, so 5,000 meters is about 15,000 feet. This is where you can start getting into issues with mountain sickness, definitely a performance decrease that will not be restored by acclimation no matter how much you acclimate there. Really high altitudes, you definitely start getting very big effects due to the hypoxia. Really, you don't see, I mean, some of the high settlements are up at about 5,200 to 5,800 meters, so that's about 15,000 feet. Most folks don't even live up that high. There starts to be issues with, honestly, reproduction and the ability to carry a fetus at some of these levels. So that's really high altitude, definitely. For our main purposes, though, when we're talking about altitude, it needs to be something greater than about 1,500 meters, which is about 5,000 feet or just under. Beneath that, you really don't see much in the way of physiologic effects. Some people will say going up to like Lake Placid and that, they notice a difference when they're running. It's probably not necessarily the case. It is at a couple thousand feet of altitude. I mean, really in New York with Mount Marcy is about the only one that's getting up to where you maybe could have some effects of altitude on you at about that 4,000 feet of altitude. But even then, you generally don't notice it at this level. It really, once you start getting above about 5,000 feet, is where you're going to start seeing definitely some acute effects of altitude on the body's physiology. So this is a list of abbreviations. I've tried to, as we went through this, go in and put some of these ones, especially like the PCO2s, the PO2s, the big A's, the little A's. I've tried to write those down the first time in this PowerPoint, but again, this is one that you might want to print out if you're going through this and looking at the PowerPoints on your own. You may want to print this page out and take a look at it so you know what it's talking about when you're looking at each of these specific abbreviations. So just to remind everybody of how we carry the gases, again, a little bit of this beginning stuff is going to be kind of a rehash of AMP2, but this is to, again, get everybody on base or on track with respiratory physiology and what's going on with it. So again, oxygen, how we carry it in the blood, oxygen is not one of these gases that dissolves well in water at all. So we carry very, very little of it in the plasma. It's less than 1% dissolves in the plasma. What that means is the vast majority of this, so the 20 milliliters of O2 per 100 milliliters of blood type of thing, that is all happening bound to hemoglobin. But in reality, 99% of the oxygen we're carrying in the body is being carried by hemoglobin. So about 1% to 1.5% dissolved, the rest of it carried on hemoglobin. Carbon dioxide, on the other hand, is carried a number of different ways, some of which is going to affect both oxygen saturation, hemoglobin saturation curves, as well as blood pH. So we carry about 7% dissolved, just as CO2 dissolved in the plasma. About a quarter of the carbon dioxide is carried on the globin portion of hemoglobin, so binds to the non-heme part, but when it is bound to this, it actually, the more CO2 that's bound, the less well it hangs on to oxygen. This is called the Haldane effect, and we'll see that there's actually a reversal of this in the tissue beds where there's actually more O2 is available, it binds hemoglobin, less affinity for CO2, so CO2 is released. You're going to see the opposite effect called the Bohr Effect actually in the tissues. And the main way we're carrying this, though, is about 70% on as bicarbonate ions in the blood. So we have a blood buffer that the CO2 is binding to and really acts as a pH buffer in our blood. And that's the main way we're carrying this, is that bicarbonate ion, that HCO2 negative. The other thing that was something we talked about in AMP2, and again, we're going to come back to on this one, we need to know a little bit about partial pressures again, and this idea of Dalton's Law. So if you remember, all the gases act independent of one another in the environment. So what CO2 is doing doesn't necessarily affect what oxygen is doing as part of its portion of the atmosphere. Same thing with nitrogen, which is the main gas in the atmosphere. The overall atmospheric pressure is a combination of all these gases. So if you have, let's say, oxygen at about 20.5% of that atmospheric pressure, if you take the atmospheric pressure times the percentage of oxygen, that's going to give you that particular partial pressure of that gas. So generally when we're writing any of these, we're going to do a P followed by whatever the gas is, so O2 or CO2. And again, each gas is going to go with its partial pressure gradient. So if it's higher in a particular area and there's a lower concentration someplace else, it's going to go down that concentration gradient. So each gas, though, acts independent of the other ones. Our atmospheric pressure at sea level is 760 millimeters of mercury. We're seeing just a little bit. We also can call that 1 millimeter mercury as 1 torr. So if you see torr, 700 millimeters of mercury is sea level, 760 torr is sea level. All the gases collectively make up that 760. So this is going to include, like I said, nitrogen, oxygen, carbon dioxide, water vapor, any other gases that are in that environment. And each one is going to be whatever its percentage is times whatever atmospheric pressure is at that particular level. So at sea level, for example, you have 24, like it says there, miles of air above you that are pressing down on this. The barometric pressure at sea level is about 700 millimeters of mercury or 760 torr. At the top of Mount Everest, you can see it's about 1/3 of that. So it's about 250 millimeters of mercury or 250 degrees torr. And again, the atmospheric pressure is a combination of all these gases. So the gases at any particular level are going to be the same concentrations. So like it says here, the atmospheric pressure, the barometric pressure varies. Air composition does not. So it's about 21% oxygen. It's a little under 0.4, it's a little under 0.04%, 0.03% CO2, and the vast majority, about 80% of the gas, just under, is nitrogen. So the pressure of oxygen is always going to be 20.93 or about 21% of whatever atmospheric is. So at sea level, atmospheric pressure is 760 millimeters of mercury. If you do 760 millimercury times 0.2093, which is that percentage of the gas there, you're going to end up with 159 millimeters of mercury for oxygen at sea level, or that is that partial pressure of oxygen at sea level. You can see, again, because there's way less atmospheric pressure on top of Mount Everest, it's about 1/3 of that. And again, whatever it is in the atmosphere is going to affect what we're able to get into our lungs. We can't fully exchange the gases in our lungs, so those partial pressures in the lungs are going to be different than atmospheric pressure. There's going to tend to be more CO2 and less oxygen in the alveoli or in the blood and the tissues than there is in the environment. But again, whatever is in that air, if you're at the top of Mount Everest, 52 millimeters of mercury there, that partial pressure means you're probably going to have way less oxygen in your lungs in terms of partial pressure, way less in your blood, way less in your tissues. So again, that total partial pressure, that partial pressure is the total pressure. So whatever that atmospheric pressure is times whatever the percentage of that gas is. So like nitrogen, 78.6% of the gas in the air, 760 millimeter mercury times 78.6% gives you 597. That is that partial pressure of nitrogen. And if you add up all the partial pressures of all the gases, it will add up to the overall atmospheric pressure. And that's basically what Dalton's Law says, is that all the partial pressures in a mixture of gases is going to be equal to, the total pressure is going to be equal to the sum of all the parts, basically. And again, how this stuff moves is it's going to move with this partial pressure gradient. So partial pressures for certain gases are going to be higher in one part of the respiratory system than another. And the gases, just like with diffusion, are going to move from areas of high concentration or high partial pressure to areas of lower partial pressure. I mean, you can think about partial pressure as kind of a concentration. Things move from higher concentration to lower concentration, higher partial pressure to lower partial pressure. And this is going to continue until they equalize. Again, assuming it's able to dissolve and that solubility is there. We're going to see certain gases that does make a little bit of a difference. But again, alveolar exchanges of these gases at the alveoli at the tissues are dependent upon these gradients. Where is there a higher partial pressure of oxygen? Higher partial pressure of oxygen in the alveoli than there is in the blood. It's going to try to move across to balance those out. Higher CO2 in the tissues than there is in the bloodstream. At the tissues, it's going to try to go the other direction, have that CO2 going in, oxygen leaving because there's less oxygen in the tissues and more in the blood. So these alveolar, all these exchanges are going to go with their particular concentration gradients. And again, because we cannot completely empty our body's breathing cavities, we have dead air space. We don't have a collapsible breathing system. Because of that, that means what is in our breathing system is always going to be a little bit different than the environment. So it's mixing the environmental air that's coming in with what was left in our dead space, which means our lungs and alveoli are always going to have higher levels of CO2 and slightly lower percents of oxygen relative to the environment. Honestly, way more CO2, a little less oxygen relative to the environment. And again, that is because we cannot empty all this. The other thing is we're going to see much more water vapor present in there because we are, one of the ways we actually lose water, as we've been talking about, is through breathing and water vapor in our breath. So like I said, within the alveoli, the percentage of oxygen is lower relative to the environment, and the percentage of carbon dioxide is much higher relative to the atmosphere. What we see in the cells, the percentage of oxygen, that partial pressure of oxygen ends up being a lot lower in the tissues than it is in the blood, and carbon dioxide, because we are taking in oxygen, using that to generate energy, and as a byproduct generating carbon dioxide. We see in the systemic cells much lower partial pressures of oxygen, much higher pressures of carbon dioxide. Because of that, we are going to see differences in the way the gases move in and out of the bloodstream at the alveoli versus the tissues. Again, like it says here, generally these levels are pretty consistent in the alveoli and in the systemic cells. Where we're going to see this is with the fact that the blood is traveling through, we're going to see this continuous exchange happening there. In the lungs, we're always kind of taking in more oxygen and exhaling off that carbon dioxide. So the partial pressures in the alveoli, unless you're holding your breath or hyperventilating or doing something weird, tend to stay pretty constant as long as you're breathing normally. Same thing with the tissues. They have a normal metabolism going on, and they generally have pretty consistent partial pressures of oxygen and CO2 in there. And again, we're continuously changing this as we bring blood in there and taking on some of this, or releasing some of the CO2, taking in more oxygen at the tissues, for example. And again, this starts to get really interesting with this Dalton's Law, is again, and this is where altitude starts to become such a big deal. We know, as I was already saying, nitrogen's about 79%, oxygen's about 21%, if we're just doing it close, about 0.03, 0.04% CO2 in the air. But what you can kind of see is, depending on what you do with that atmosphere, the partial pressures can differ. As you go higher in altitude, you have less atmosphere above you, and therefore you have less atmospheric pressure. If you have less atmospheric pressure, and each of those gases are always a percentage of atmospheric pressure, you're going to have less of any particular gas in your atmospheric air. So when you get up to 10,000 feet, for example, the atmospheric pressure is 523 millimeters of mercury, not 760. Because of that, the atmospheric oxygen that's available, the partial pressure there, is about 110 millimeters of mercury, and because we don't fully exchange the gases in our lungs, what actually gets to your alveoli is only about 67 millimeters of mercury in the alveoli. You can see as you start getting up to 20,000 feet, which is one mountain in the U.S. that Denali up in Alaska is a little over 20,000 feet, but you can see at 20,000 feet, atmospheric pressure is about half, little over half. Because of that, and you can start seeing, you get down to that there is less than half of that in the alveoli. So it's 70 or 60 millimeters of mercury partial pressure in the environment. 73 millimeters of mercury in the environment from that 350 millimeters overall. And then you can see it's only about 40 millimeters of mercury partial pressure of oxygen in the alveoli. And then finally, when you get to way high altitudes, 50,000 feet, there's actually not enough oxygen to keep you alive. really it gets to be about 26,000 feet is considered to be the death zone. Above that, you are in the process of dying because there's not enough oxygen. It just, you're not going to die immediately, depending if you've acclimated or not. But there's not enough oxygen in the air above 26,000 feet to live there or to be up there indefinitely. But once you get up to like 50,000 feet, you can see there, very little atmosphere above you in terms of pressure. It only gets to be in about 2 millimeters of mercury partial pressure in the alveoli. So almost no oxygen available to you in the environment. And this is why if you're on a plane and there's a decompression, why that can be a big issue. You can lose consciousness and die from that. The other thing that's kind of interesting, we may talk about this as we get closer to the end. We're at about week 10 here. This is going to take us a couple weeks to get through this. We may be able to talk a little bit about pressurized gases and breathing pressurized gases. But if you're breathing with a regulator underwater, because water is more dense, atmospheric pressure is going to go up a lot quicker. So if you're about 33 feet underwater, that is equal to another atmosphere of pressure. So if you're breathing through a regulator with a gas that is regulating the pressure of gases going into you, for every 33 feet, you're going to have another atmosphere of gas. But what that means is if you're breathing normal pressurized gas in a tank, and it's just not any special mixture, but just atmospheric mixture in there, the double the atmospheric pressure would be 1,500 about millimeters of mercury, which you can see starts getting you much more oxygen into your, in terms of partial pressure. The other issue that this becomes is it also gives you a lot more nitrogen. And that's where this can be a problem. But as you can see, if you go down to, like, let's say 90, 100 feet underwater, you're under 3 atmospheres of pressure. And that gas is going to be a little bit different. You have 3 more atmospheres of pressure. So you can see if you came up really quick then, you are going to have 3 times the amount of nitrogen in your blood. And if you relieve that pressure too quick, that's where the bends happens. That decompression sickness happens. So again, torr, I just wanted to put this one up here. Torr is 1/760th of normal atmospheric pressure. Basically, a torr and 1 millimeter mercury are the same measure. But a lot of times when you're talking about this stuff, you'll see torr used. So that was just kind of letting you know that. I've already mentioned it a little bit, but that's the conversion. 1 torr is 1 millimeter of mercury. Again, it gets kind of interesting when we start doing this. So we've talked a little bit about the Haldane effect already, but the fact that you really have high partial pressures of oxygen in the lungs, this affects how hemoglobin and how the blood holds on to CO2 and hydrogen ions. So higher levels of oxygen tend to lead to a greater release of CO2 and hydrogen ions from hemoglobin at this area. We see an opposite effect in the tissues, a Bohr effect, where you have these high levels of CO2 and hydrogen ions in the muscle area surrounding the capillaries there that tends to cause hemoglobin to let go of oxygen and stimulate its release. So it's kind of neat in that sense how you have these counteracting effects that help with the loading and unloading at these different areas, at the alveoli and at the tissues where we're picking up and dropping off some of these different respiratory gases. And again, this is kind of showing where the PO2 and the POCO2 are kind of changing here. But again, kind of gives you that idea. And you can kind of, we'll come back to some of these exchanges and what the gases look like along the way here. But the main thing is here, because as you go up in altitude, you have less atmospheric pressure. In a simple sense, that means you're going to have lower partial pressures of oxygen. Lower partial pressures of oxygen means lesser gradients, and the amount of oxygen that's going to get in the bloodstream is going to start changing depending upon how high of altitude you go up to. And again, this is kind of showing you some of these things here, different areas and the different torr at some of these different levels here. But this is at like 5,000 meters is about the highest human permanent habitat. You can see Pikes Peak is about 14,000 feet. So this is kind of showing you the altitude and the different atmospheric pressures, but you can kind of see at sea level 760. When you start getting to Pikes Peak, it's probably about 450. You can see the highest kind of human populations are going to have atmospheric pressures probably just under 400. And then you can start seeing, once you start getting up way higher, Once this can start being an issue, sooner or later you can go up so high that just your normal body temp is enough to, if you get to a low enough pressure, that you can have your blood actually, the gas is bubbling out of your blood at body temp. So why water boils at the temperature it does has a lot to do with atmospheric pressure. If you go higher up, if let's say you're up in the Rockies, water does not actually boil at the same temperature because those gases, there's less pressure keeping those gases in that solution. So it takes less heat to release them. You can actually see that if you start reading cookbooks and doing some of this stuff. Baking and a lot of these other things, the chemistry of it and the difficulty of it gets a lot harder as you go up in altitude. And this is just a nice little table showing you the changes in this at different heat heights. But you can kind of see what the overall atmospheric pressure would be at 18,000 feet. Basically what's in the alveoli, what's in the arteries, CO2 levels. But the main thing you can kind of see, because the atmospheric pressure changes, the alveolar pressure, partial pressures are going to get much lower as you go up in altitude, which means what we can carry in the arteries gets less, which again is going to be an issue, especially if you're doing anything active. But just in some cases, just being alive starts getting difficult as you go up higher and higher. And again, simple sense, higher altitude equals lower partial pressure of oxygen. You can see here the partial pressure of oxygen at 4,300 meters is much lower in the gas we're breathing in the alveoli, in the arteries, you don't see as big of amount here because again we're dropping off some of that to the tissues. So the venous blood, they tend to be similar, but you can see even at 4,300 meters, at sea level, we don't unload all that oxygen. There's still way less as you go up in altitude, even in the blood that's already delivered oxygen to the tissues. And again, just one more graph kind of showing this. Again, showing that these oxygen levels as you go up in as you go up in altitude or go lower in pressure, partial pressures of oxygen tend to get lower and lower and lower. And again, this, as we'll see, starts becoming an issue sooner or later as you get up higher. And this has a lot to do with hemoglobin saturation. Certain amounts of oxygen or partial pressure are necessary to fully fill up the hemoglobin in the blood. We're going to see at sea level, we are definitely saturating our hemoglobin full of oxygen. It takes, once you start getting up to about 5,000 feet is where you're going to start, like I said, seeing a noticeable difference. But again, if you were breathing in gases of the same concentration, this is kind of showing you at these different atmospheric, at these different altitudes, what would be the corresponding actual percentage of oxygen compared to the normal environment. So at sea level, it's about 21%. Like I said, it's still 21% of the air at 18,000 feet, but corresponding percentage of O2, it's about half as much oxygen available to you is what it's really kind of saying on this one. It's kind of giving you that idea that there's actually way less oxygen as you get up to that 20,000 feet. And you can see, add another 10,000 feet to that, you're looking at about 1/3 the oxygen level as you get up above that 26,000 feet where people are climbing Everest, for example. So that is, again, just kind of showing you, to me, the simple thing, how much oxygen is available at altitude. What we're going to start looking at on these next ones is, what does that mean for the body? I mean, in a simple sense, we know we need oxygen to do our normal respiratory, our normal metabolism, to generate our ATP. So you can kind of start seeing, as you go higher up, the ability to do that is going to become lesser and lesser because we're having less partial pressure of oxygen available. This is going to become more of an issue, as we'll see later on. So I'll see you next time.